Look up at any modern commercial building, that flat roof. Engineers calculated every stress point. Computer models simulated every load. Steel and concrete engineered to exact specifications. Now look at a medieval timber roof. No calculations, no computers, just wood, geometry and centuries of trial and error. The modern roof fails in decades. The medieval roof stands for 800 years. This is not romantic nostalgia. This is measurable, mechanical reality. In 2006, a 6-year-old building in Poland collapsed under routine snowfall. 65 people died. The snow load was well within design limits. The structure failed anyway. That same winter, a 500-year-old timber palace, 800 kilometers away, stood untouched. Same storm, same snow, zero damage. Something happens when you build with principles instead of calculations. When you work with gravity instead of fighting it. When you create joints that tighten as they age, not loosen. Medieval carpenters understood something we forgot. Not through theory, but through failure. Collapsed barns meant starvation. Failed roofs meant death. The buildings that survived encoded that knowledge. 3 principles. Principles that work anywhere, in any climate, with any materials. Today, we are going to rebuild that knowledge, principle by principle. Section 1. The geometry of survival. Look at any medieval building that has survived 600 years. The first thing you notice is the roof. Dramatically steep. This was not style, this was survival. Modern engineers fight snow with strength. They calculate load capacity, add steel reinforcement, try to hold the weight. Medieval carpenters used a different strategy. They shed it. Think about a playground slide. On a gentle slope, friction holds you. On a steep slide, gravity takes over. You slide without effort. Snow behaves the same way. Engineering research confirms snow begins self-shedding at 30 degrees, active sliding at 45 degrees. Medieval builders consistently used angles between 45 and 60 degrees. Here is what makes this brilliant. They discovered these angles without protractors, without calculations. They used a chord and proportional folding. Each fold created a ratio. Each ratio produced an angle. This created 5 standard pitches across medieval Europe. The same angles appear in buildings from the year 980 onward. The choice followed the material. Thatched roofs required at least 50 degrees. Below that, rain penetrates. Stone slate needed similar angles. Heavy materials need steep slopes. Borgund Stave Church in Norway demonstrates this perfectly. Built in 1180, 844 years ago. The roof uses multiple tiers cascading down. Each tier sheds snow independently. The lowest sections are 45 degrees. Upper sections steeper. Snow slides off each level before it accumulates, before it builds dangerous weight. 844 years later, the system works perfectly. Westminster Hall in London uses the same principle. Built 1393 to 1401. The roof spans 68 feet, about 20 meters. The largest medieval timber roof in Northern Europe. The pitch is 52 degrees, steep enough to shed London weather, strong enough to survive the Great Fire of 1666, solid enough to endure World War II bombing, 631 years standing. But steep angles alone do not explain this survival. There was something else, something in how they built the structure itself. In 2012, after a massive Italian snowstorm, engineers inspected the Ducal Palace. They expected stress damage, microfractures, signs of strain. They found nothing. One engineer said the roof seemed designed to work with snow, not against it. He was right. But he did not understand why. The secret was not resisting the weight. The secret was where the weight traveled. Medieval carpenters figured out something modern engineers often forget. Gravity is not your enemy if you know where to send it. The steep pitch cleared most snow before it became a problem. But when storms deposited more than could slide away, the structure had to handle the load. And that is where the second principle came into play. A principle that turns gravity into structural stability. If you are realizing that we abandoned something that actually worked, hit that like button. And if you want to see more forgotten engineering that could change how we build today, subscribe, because what comes next shows why these principles matter more than ever. Section 2. Triangles that cannot fail. Push on a square and it collapses. Push on a rectangle and it folds. But push on a triangle and nothing happens. The only way to change a triangle is to change the length of its sides. This is mathematical law, and medieval builders understood it completely. Every successful medieval roof used triangulation. The specific designs varied, but the principle never changed. In Western England and Wales, carpenters used cruck frames, massive curved timbers extending from ridge to ground. Each pair formed a giant A-frame. The genius was the load path. Most buildings use walls to hold up roofs. The roof pushes down and outward. This outward thrust constantly tries to push walls apart. Cruck frames eliminated this. The roof weight flowed down the curved timbers directly into the ground. Walls became weather screens, not load-bearing elements. This made cruck buildings incredibly stable. The heavier the load, the more the weight drove timbers into earth. A cruck frame under snow load was more stable than without snow. Laycourt Barn proves this. Built in 1344, 681 years ago, the largest cruck-framed building in Britain, span of 34 feet, each timber pair from a single oak tree split down the middle. The barn has survived almost 700 years, largely unaltered. No spreading, no sagging. The system holds as firmly today as in 1344. But crucks were regional. Most of Europe never used them. They had different triangulated systems that worked just as well. In Scandinavia, stave churches used vertical posts with scissor beam roofs, two rafters crossing like scissors, a collar beam tying them together. Pure triangulation. Borgund shows this clearly. The scissor beams prevent sideways movement. Load path perfectly direct. From ridge to scissor crossing, to posts to foundation. 844 years without failure. Westminster Hall used something more sophisticated. The hammer beam roof. Short horizontal beams projecting from walls, supporting vertical posts, which support curved braces, which support main rafters. A web of interlocking triangles, each element reinforcing the others. The design creates a 68-foot clear span with no columns, just open space. Master carpenter Hugh Herland designed this in 1395. The largest clear span timber roof in Northern Europe. It has stood 631 years. In France and Germany, builders used king post and queen post trusses. Vertical posts connecting ridge to tie beam, creating rigid triangles. The designs varied, materials varied, traditions varied, but triangulation never changed. When snow accumulates on a triangulated timber frame, the weight compresses the structure. Compression is exactly what wood handles best. Grain runs along the length. Compression along grain is incredibly strong, so snow weight actually stabilizes the frame. It drives connections tighter. It seats joints more firmly. The structure under load is more rigid than without load. This is opposite of how modern flat roofs work. Snow sits as dead weight. The structure fights against it. Eventually, something gives. Medieval triangulated roofs turned that weight into stability. The more it snowed, the stronger the structure became. During 2010 to 2011 winter, nearly 500 buildings collapsed across northeastern United States. The storm was a 25 to 50-year event. Not extraordinary. Medieval buildings across that region stood undamaged. Buildings 600, 700, 800 years old. Same snow. Zero failures. The difference was geometry, triangulation, load paths that worked with gravity. But geometry and triangulation were not enough. There was a third principle. Something in how pieces connected that made joints stronger as buildings aged. Section 3. Connections that tighten with time. In 2014, a restoration team worked on Laycourt Barn. They needed to document original construction before repairs. They expected loose joints. 670 years of expansion and contraction. Surely connections had loosened. They found the opposite. Joints were tighter than when built. This made no sense. Wood shrinks as it dries. Nailed joints loosen. Every carpenter knows this. Old wood means loose joints. But these joints had tightened. The team measured gaps. There were none. Timber shoulders pressed so firmly against mortise faces you could not slide paper between them. How? The answer was in the pegs. In a technique called drawbarring, medieval carpenters built massive structures using no metal, no nails, no screws, just wood locked to wood with wooden pegs. The foundation was mortise and tenon, a tongue on one beam fitting into a hole in another. But medieval carpenters added refinement. Here is how draw boring works. Cut the joint precisely, assemble it, drill a hole clean through both pieces, mark where the drill touched the tenon, take it apart. Now the clever part, drill a second hole in the tenon, but offset about 3 mm closer to the shoulder. The holes are deliberately misaligned. To assemble, drive a tapered oak peg through the offset holes. As the peg passes through, it forces holes to align. This physically pulls the shoulder tight. The peg bends slightly, creating spring tension. The joint is clamped with enormous force. The Timber Frame Engineering Council documented this in 2020. Evidence shows use by the 13th century in England, but the real genius appears over decades. Medieval carpenters worked with green oak, freshly cut, unseasoned. They knew it would dry and shrink. In nailed joints, this is disaster. Wood pulls away, connection loosens. But in drawbar joints, shrinkage has no negative effect. Wood shrinks across width, not length. The offset peg maintains constant tension. As timber seasons and hardens over years, the joint remains tight. A nailed joint is strongest on day one, then weakens. A drawboard joint reaches full strength after seasoning and maintains it for centuries. French timber framers added one detail: they left pegs slightly proud, sticking out a few millimeters. Decades later, a carpenter could tap the peg deeper, retightening the joint. A structure built for adjustment across generations. Westminster Hall proves this. Hammerbeam connections use complex drawboard joints. Some connect 3 or 4 timbers, multiple pegs per joint. 631 years later, those joints are still solid. Steel reinforcement was added in 1914, not because originals failed, but because engineers worried. The original joints never needed repair. This technique was universal. English crucks used it, French colombage, German Fachwerk, Scandinavian stave churches. The method crossed all boundaries because it worked. Modern timber framing has rediscovered this. The Timber Framers Guild, founded 1985, studied surviving medieval structures. They reconstructed techniques. Today they teach drawbarring for practical advantage, not historical reenactment. A joint that tightens with age. A joint requiring no metal, a joint lasting 600 years. The restoration team at Lee Court understood when they measured those impossible joints. The barn was not falling apart. It was settling into final form. The form it would hold for another 600 years. 3 principles. Steep angles to shed snow. Triangulation to prevent deformation. Joints that adapt and strengthen. But these did not exist in isolation. They were part of a larger system. Section 4. The material intelligence. Medieval builders did not impose designs on materials. They asked what the material wanted to do, then built systems that allowed it. This sounds philosophical. It was practical survival. Take roofing materials. The choice determined everything. In Scandinavia, turf roofs dominated. These sound primitive. They are sophisticated multi-layer systems. Construction started with birch bark. 6 to 16 layers, overlapping like shingles. Naturally waterproof. On top, 2 layers of turf. First grass, side down. Second grass, side up. Roots grew together, creating a living mat that self-repaired. The weight was enormous, about 250 kilograms per square meter at base. With snow, 400 to 500 kilograms per square meter. Why build a roof this heavy? Because weight was the design. The weight compressed log walls, sealing gaps, making structures airtight. In winter, snow added more compression, better insulation. Buildings became warmer as snow accumulated. Borgund Stave Church was built to handle this. The multi-tiered design sheds excess snow. Steep pitch ensures sliding. Triangulated scissor beams handle the load. Materials, geometry and structure worked as one. In England, thatched roofs dominated for 1,000 years. Well-built thatch lasted 50 to 60 years per layer. Traditional practice only replaced outer weathering coats. Base layers remained. Over 250 thatched roofs in southern England have base coats applied over 500 years ago. The innermost archaeological layers preserved within the structure. Cotswold stone slate required 50 to 55 degree pitches. Heavy tiles needed steep angles. Welsh slate could use gentler slopes. The material absorbed almost no water, less than 0.6%. This prevented freeze-thaw damage. Welsh slate roofs from the 1300s still function today. The pattern is clear. Medieval builders did not force materials to comply. Material dictated design. Turf required specific structures. Thatch required specific pitches. Stone required specific angles. Modern construction often reverses this. Architects design forms. Engineers force materials to fit. Medieval builders listened to what material could naturally do and built around that. This partnership created structures that lasted because they respected the nature of their components. Work with nature, not against it. Simple principle. Centuries of survival. Section 5. When modern systems fail. Remember Katowice? 65 dead in a building 6 years old. That was not unique. That was a pattern. January 18, 1978. Hartford, Connecticut. The Hartford Civic Center, 5 years old. At 4:15 a.m., the roof collapses. 140 tons of steel and concrete crash down. The arena was empty. Pure luck. No deaths. Snow load was 14 to 19 pounds per square foot. Far below design specifications. Engineers found the space frame had underestimated its own dead load by 20%. The structure was failing before snow fell. December 12, 2010, Minneapolis, the Metrodome. The roof was inflated fabric, a typical Minnesota snowstorm. The fabric accumulated 9 pounds per square foot. It tore. It collapsed. 9 pounds per square foot. Less than some medieval thatched roofs weighed before any snow. The building was 28 years old. January 3, 2006. Bad Reichenhall, Germany. Ice rink roof collapse. 15 dead. Snow load, 34 pounds per square foot. Building 34 years old. Moisture had compromised laminated beam glue. The problem was known. Repairs delayed. 15 dead from deferred maintenance on a 34-year-old building. Same winter. Urbino, Italy. Ducal Palace stood untouched. 500 years old. Zero damage. Nearby modern buildings failed. San Francesco Convent, partial collapse. San Bernardino Convent, partial collapse. Capuchin's Church, complete roof failure. All 20th century structures, built to code, well maintained, they failed. The 500-year-old palace survived. Winter 2010 to 2011. Nearly 500 documented roof collapses across northeastern United States. The storm was not extraordinary. A 25 to 50-year event, twice per century frequency, 500 failures. Most built after 90, most built to modern code. Meanwhile, Great Coxwell Barn stood since 1292, 733 years. Lee Court Barn since 1344. Westminster Hall since 1395. Borgund Stave Church since 1180. What is the difference? Modern design fights nature with calculated strength. Materials engineered to exact specifications. Structures with minimal safety margins to save cost. This works perfectly within design parameters. Step outside those parameters and the system fails catastrophically. No graceful degradation. Total collapse. Medieval design worked with nature, used gravity to shed load, used triangulation to prevent deformation, used joints that adapted, built massive safety margins through centuries of observation. They over-engineered everything because they could not afford to fail. A collapsed barn meant starvation. A failed roof meant death. Stakes were absolute, so they built with redundancy, multiple load paths, systems that could lose elements and still stand. Modern engineers optimize for efficiency, for minimum material use, for maximum cost savings. This creates structures that perform brilliantly when everything goes right and fail completely when anything goes wrong. The cruel irony of Texas 2021 was that most homes had fuel available, natural gas lines pressurized, but modern furnaces require electricity. No electricity meant no heat, even with fuel present. Single point of failure. Medieval peat systems had no dependencies. Medieval timber roofs had no single point of failure. Remove one element and the system still functioned. That is the difference between optimization and resilience. Know a builder or engineer who needs to understand this? Send them this video. Because what we have forgotten could save lives when systems fail, and they will fail. Section 6. The universal principles strip away the regional differences. Ignore whether the frame is cruck or stave or hammer beam. Look past thatch or slate or turf. What remains are 6 universal principles that work anywhere, with any materials, in any climate. Principle 1. Work with gravity, not against it. Steep angles between 45 and 60 degrees turn snow weight into the force that removes it. At 52 degrees, gravity overcomes friction. Snow sheds itself. No mechanical systems, no human intervention, just geometry. Principle 2. Triangulation prevents deformation. A triangle cannot change shape without changing the length of its sides. As long as those sides hold, the shape holds. Medieval builders used crucks in Wales, stave construction in Norway, hammer beams in London, king posts in Germany. Different solutions, same principle. Principle 3. Joints must adapt to change. Wood shrinks and swells with humidity and temperature. Fight this and joints fail. Accept it and design for it. Draw boring creates connections that maintain tension as wood seasons. The joint works with natural processes, not against them. Principle 4. Materials dictate design, not the reverse. Thatch needs 50 degrees minimum. Stone slate needs steep angles. Welsh slate can use gentler slopes. The material determines the geometry. Medieval builders let materials perform their natural function. Principle 5. Redundancy ensures survival. Medieval frames have multiple load paths. If one element weakens, others carry the load. No single point of failure. Modern engineering optimizes for minimum material and maximum efficiency. Medieval engineering optimized for maximum survival with massive safety margins. Principle 6. Observation beats calculation. Medieval builders had no software, no finite element models, no computer simulations. They had buildings that stood and buildings that fell. They studied both. They adjusted. They refined over centuries. Modern engineers trust calculations. They build what software says will work. Then they are surprised when reality disagrees. Medieval builders trusted what they could see, what they could measure, what 300 years of construction had proven. They built conservatively with massive margins for error. These 6 principles are not medieval secrets. They are fundamental physics. Gravity has not changed. Triangles still cannot deform. Wood still shrinks as it dries. Materials still have natural properties. We did not lose this knowledge through time. We chose to abandon it for efficiency. The question is not whether these principles still work. Borgund Stave Church proves they work after 844 years. Westminster Hall proves they work after 631 years. Lee Court Barn proves they work after 681 years. The question is whether we are willing to remember them. Before more roofs collapse. Before more people die in buildings that should have protected them. Tauf to Eternity, January 28, 2006. Katowice, Poland. 65 people died when a roof collapsed under 34 pounds per square foot of snow. The building was 6 years old. 800 kilometers away, the Ducal Palace stood untouched. 500 years old. Same storm, same snow, 0 damage. The difference was not materials, not technology. The difference was principles. 3 principles. Medieval carpenters discovered through centuries of trial and error. Steep angles that shed snow before it becomes dangerous. Triangulation that prevents deformation under any load. Joints that adapt and strengthen with time. These principles are not romantic nostalgia. They are proven engineering that works across 800 years. Through storms that collapsed modern buildings built with steel, concrete, and computer analysis. We have tools medieval carpenters never imagined. We understand physics and material science at levels they could not conceive. We have materials stronger than anything in medieval Europe, and our buildings fall down in decades. The lesson is not though, old is better. The lesson is that principles are timeless. Geometry does not change, physics does not change, triangles still cannot deform. We do not need to abandon modern knowledge. We need to combine it with ancient wisdom. Build with modern materials and medieval principles. Use computer analysis to validate what centuries proved. Optimize not for minimum cost but for maximum survival. Build roofs that will shed snow for 800 years. Build like you believe the future matters. Not for profit, not for efficiency, for eternity. The next storm is coming. When it does, geometry will matter more than building codes. Triangulation will matter more than spreadsheets. And the principles that kept people alive for 800 years will matter more than the shortcuts that let buildings fail in 6. The medieval carpenter who built Lee Court Barn in 1344 is long dead, but his roof still stands, still sheds snow, still protects. That is the measure that matters. Not cost, not speed. Whether it will outlive you, whether it will protect people you will never meet, whether it is built for eternity. The knowledge exists. It never disappeared. You can see it in Borgund, in Westminster, in Lee Court. Every time you choose to build with these principles, you vote for permanence over profit. Katowice taught us what happens when we forget. Westminster teaches us what happens when we remember. The question is, which lesson we choose to learn.